All right, hello and welcome to our first video about chemical reactions. But before we get into that, I wanted to point out that when it comes to calculators, everybody really thinks that the buttons are so important. But it's what's inside that counts. You're welcome. Okay, let's get on with it. So in order to understand chemical reactions, we're going to have to do some review. So this is stuff we've already gone over about naming chemical compounds that came from our unit on bonding. So my hope is that this should be very familiar and should be something that will make more sense the second time around. So there's three things that we want to kind of go over just in this video before we start talking about reactions. And those are chemical formulas, the types of bonds that form between atoms, and how we name covalent and ionic compounds. So let's review briefly how we do that. And as a reminder, here's our example molecule, CH810H10N4O2, otherwise known as caffeine. That's why it's spelled out in coffee beans. Okay, so what's a chemical formula? Chemical formula is something that tells you the number of atoms of each element in a molecule or compound. And that's what we're seeing right here with our caffeine. It tells you that we have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. These little numbers, which are below and to the right of the letters, are subscripts. They're subscripts, and that tells you exactly how many atoms there are of each element present. So in a molecule of caffeine, we can tell that it has 8 atoms of carbon. It so happens that if atoms are in parentheses, if there were some parentheses in here, there would be another number, and we would multiply the numbers inside and outside of the parentheses. We'll see more of what that means later on, but for now, let's just focus on this is how we write out a molecule so that we know how many atoms of each element are present, and that is called a chemical formula. Pause the video if you need some more time to finish taking notes. Okay, then another thing that we learned with chemical formulas were what are called coefficients. And coefficients, just like you would have in math, are numbers that you put to the left of a molecule or compound's chemical formula. And it tells you how many of those molecules or compounds are present. So again, this is a caffeine molecule. We know that there's 8 carbons in it. But if we put a 3 to the left, we know we have 3 caffeine molecules present. And so the number of total carbon atoms present is 3 times 8. The number of hydrogen atoms present is 3 times 10, etc. So you multiply everything by the coefficient to determine the number of atoms present. We've got 3 of these. That means we've got 24 of these. 3 of these, 30 of these. And that's going to become pretty important when we get to balancing chemical equations in a different video. Okay, then another reminder. Another review is what are the major types of bonds that we can have between atoms. And we talked about 3 kinds. We talked about covalent, ionic, and metallic. Metallic is when it's nothing but metal getting together, and that's not really something that we're paying attention to in this class, but just so you know. The ones that we're really focused on are covalent. Those are 2 nonmetals sharing electrons, and ionic is between one metal and one nonmetal, and that's when a metal gives and a nonmetal takes the electrons, because bonding is all about those electrons. And that's why a covalent bond yells at an ionic bond and says, "Didn't anybody ever teach you to share?" Right. Pause the video, finish your notes, make sure you understand why that joke is funny before proceeding. All right, so how do we name covalent compounds? Again, something we went over before. Let's go through it briefly again. So if we have a covalent compound, that means we have 2 nonmetals involved. For example, here, nitrogen is a nonmetal, oxygen is a nonmetal. So if we know we have a covalent compound, here's how we're going to name it. We're going to take the first element and just put its full element name down. So this is nitrogen. We're going to put down nitrogen. We're going to take the second element and we're going to remove the last syllable of its name and replace it with IDE. So oxygen, we take the OX and we remove the YGEN, the gin part of it, and we replace it with IDE, so it becomes oxide. And then we have to use prefixes to show how many atoms of each element are present. And you've got your prefix list here. The most common ones that we use are mono for 1, di for 2, tri for 3, tetra for 4. So for this one, because there's one oxygen, we're going to put monoxide, or monooxide, but we would pronounce it monoxide because there's not a second O. What we don't do is we don't put mono in front of the first one when there's only one of it present. So we don't say mononitrogen, we just say nitrogen monoxide. We do use the prefixes for other ones. So if it's N2O, we say dinitrogen monoxide. And then you can see some other examples. If we have 2 chlorines and 7 oxygens, we're going to call it di for 2, chlorine, hept for 7, oxide. Make sure you have this list of prefixes handy somewhere. If you can't get it here, pause the video or otherwise look it up from your notes previously. Make sure you know which prefixes mean which numbers. All right, when it comes to ionic compounds, we are talking about one metal and one nonmetal. One metal and one nonmetal. So for this example, we've got aluminum, that's a metal, sulfur, that's a nonmetal. How are we going to name it? First, what we have to do is figure out how do we put it together in the right ratios. So ionic compounds come together in ratios that make them neutral. So first we're going to find the charges for each of the elements involved. And how do you find the charges? Well, each element is going to form a certain kind of ion, and we can figure that out by looking for the charge that's listed above the column in your periodic table. So for example, everything on the very left-hand column should have a +1 above it, and you know that those guys will form +1 charges. Or, if it's not one of the ones that we can predict from the table, if it's a transition metal, we're going to have the charge given to us. So if it's iron, for example, you won't know from the periodic table, so you'll have to see, oh, this is iron with a +3 charge. The charge on one element becomes the subscript on the other. And so that's what we do. It's called the drop and swap, right? We take this 3+ that we figured out aluminum would have because we looked it up on the table, and we give that 3 to the sulfur. We take the 2- that we know sulfur would have from the periodic table, and we give the 2 to the aluminum. So we know that when aluminum and sulfur come together, they form this Al2S3, 2 aluminums and 3 sulfurs coming together. Pause the video, review that if you're not comfortable with the drop and swap yet. Okay, so how do we then make the name of it? Well, we take the 2 ions. The cations, that's going to be your positively charged or your metal ion, and you take your anion, that's going to be your negatively charged or your non-metal ion. You take the cation's name, and then you take the anion's name and give it an "ide" at the end. No prefix is necessary, but we still use this "ide" thing on the second part. And so that gives us NaCl turning into sodium chloride. So Na is sodium, Cl is chlorine, we change chlorine into chloride. CaCl2, that's calcium, and Cl chloride, right? We don't need to worry about this 2 when we're making the name because we don't do that in ionic compound naming. We do use our Roman numerals if it's a transition metal. So if I see ZnO, I can drop and swap and say, well, because the O forms a charge of -2, that's what the periodic table tells me, the zinc must be a +2. So I put this little 2 Roman numeral in parentheses here, so I can call it zinc 2 oxide. All right, and there's another thing that we need to know for our ionic compounds, and that's polyatomic ions. Polyatomic ions. What are polyatomic ions? They're these atoms in specific ratios that stick together, and as a unit, they'll go and bond in ionic compounds. As a unit, they'll go bond in ionic compounds. So for example, phosphate is this thing called PO4. So it's a phosphorus and 4 oxygens. And as a group, they have an overall charge of -3. And that PO4, with its overall charge of -3, will go stick onto some positively charged things to make an ionic compound. These are the 12 you need to have a list of. No need to memorize, but you need to have a list of so that you can figure out what they are, either by seeing the formula or by seeing the name. Note on something that's been confusing in the past, hydrogen carbonate or bicarbonate, right? So this is 2 different names for HCO3-, hydrogen carbonate or bicarbonate. Okay, and when we name ionic compounds that involve polyatomic ions, we do the same thing, but we actually don't need this IDE. We don't need the IDE. And if we have more than one polyatomic ion involved, we're going to put the polyatomic ion in parentheses. Here's some examples. NaHCO3. Na is sodium, right? And then when I see this many things, I should look at my polyatomic ion list, and I can see that HCO3 is either bicarbonate or hydrogen carbonate. So I'm going to call it sodium bicarbonate, right? Calcium nitrate, well, that's calcium and 2 of these NO3s, 2 of them. See the subscript there. So that means there's actually 2 of them present, and I'm going to call that calcium nitrate. That 2 doesn't actually change the name. Then we've got copper sulfate. So copper, Cu is copper, SO4 is a polyatomic ion that has a charge of -2. I looked that up on my polyatomic ion list. So that -2 means that the copper has to have a charge of +2. I can drop and swap and figure that out. So it becomes copper and then Roman numeral 2, sulfate. Sulfate being the name for SO4 as a polyatomic ion. If that's a little confusing, pause the video, rewind, watch it again, or finish your notes. All right, so that rounds it out for our review of how you name compounds and how to tell the difference of it. Next up, we are going to start to figure out how you write out chemical reactions.